Hello everybody, and welcome back to the next video in our calculus journey. So this video follows up the last one, which was covering double integrals over nice, easy rectangular regions. And this video covers double integrals that happen over general regions. And so we're going to kind of investigate, what does this mean? What do we mean when we talk about general regions, right? What is this? And so what I mean is, maybe it's best to lead by an example. So let's say, for example, let's see, evaluate the double integral of the function. So we'll just make up a random one on the spot. F of xy equals, 2x squared plus y. And we're going to do it over the region that is trapped, let's see, by the line, by the line, let's see, y equals x plus 1. We'll do x equals 0, x equals 2, and y equals 0. So this seems like a lot, but as I always suggest, the best thing to do to try and really see what's going on here is to draw a sketch, and that is exactly what I'm going to do. So here is my little axes, here's my x, here's my y, here's my z. My function kind of exists somewhere up here. Again, it's just some general function, f of x, y. And now I'm going to try and take a look at, this region. What is this region? Because we know that this is going to be some double integral, right? We know it's going to be some double integral of our function, right, with a dx dy. So of our function 2x squared plus y, with either, a dx dy or a dy dx, right? One or the other. Because again, height times length times width, doesn't really matter which order you do it, as long as we have all the pieces. So the question is, what are the bounds, right? What are these bounds? I have no idea what these are. How do we go about doing that? And so this really just comes from, us being able to understand this part of the question, right? We need to be able to sketch this region of integration right here. And so I am going to try and do just that. So we have to kind of think of it in a slightly different way if we're looking at it in 3D, but perhaps instead of trying to look at it in 3D right off the rip, I will simply try and just, figure out what this would look like if we were looking at our region of integration in 2D, because this is a 2D region of integration. So there's my x and y. So let's put some things. So let's see. X equals 0. Well, that's just this entire line right here. Right? There's x equals 0. How about x equals 2? X equals 2 maybe is right here. So maybe I'll put this right here and say, let's just call this x equals 2. Maybe we'll call the y equals 0. Maybe we'll use in yellow. So there's a line y equals 0. And then the line y equals x plus 1. Hopefully we know kind of looks like a line that does something like this. So there's y equals x plus 1. So our region of integration, the region of integration that we care about, is going to be this space right here. And so what does this look like in 3D? You just kind of have to think about it in a slightly backwards way, but right, there's our line, y equals x plus 1. There's x equals 0. Here is x equals 2, right? Here, I'll label these x equals 2, x equals 0. There's y equals 0. And here's our line, y equals x plus 1. And the region of integration that we are concerning ourselves with is this right here. That is what we want. We want to integrate over that. So if it helps you to think about this as volume, we want the volume of the shape that exists above this region and above this region only, right? This is what we are looking for here. Okay, we want something that looks kind of like this. I don't know, something like this. That's what we want. And so right, we already have pretty much 90% of the problem done. We know how to set this up. It's a double integral. There's our function, dx dy, dy dx. And so we just need to figure out the bounds. And so the question is, what this really boils down to, and I'm going to have to scroll up just a little bit for this. So what this question really boils down to is how do we describe this region of integration, in terms of x and y, right? In terms of x and y. How do we go about doing this? What could we put? And you can start with either one, but I'm just, for the sake of learning, I'm going to say, well, let's start with bounding the x values, right? Let's try bounding x first. Okay, you could do a y first, it really doesn't matter, but I'm just choosing to do x first. So if I wanted to, the goal is to describe this region right here, that's what we want. What do my x values go between? And hopefully it doesn't take too much to see that, well, a good guess would be that x goes from 0 to 2, right? And what that would give us, now this doesn't give us, the region we want right away. What it gives us is basically all of this, right? Because this is the region, this is an infinite region. If all I do is specify that one of the bounds is from x goes from 0 to x goes to 2, then when we're trying to do this integral, right, remember that when we do an integral, what are we doing? We're picking a point, we're drawing a rectangular prism above that point, right, and we're moving it left and right and up and down and stuff like that. So we pick a point right here, and we are saying, I'm going to calculate the volume of the rectangular prism that exists right above this point. And by choosing x goes from 0 to 2, you're saying I am going to do this for every x value from 0 to 2, right? I'm going to slide x from 0 to 2. And this is good, but, it also allows me to pick x's up here because technically, this box over here would go from 0 to 2 as well, right? And so clearly we need one more bound here. We need something that's going to stop us from going too high in the y direction as well. And so if we take a look at the y bound, so, now the y bound, what does y go between? Well, the lower y bound is the easy one, right? It's easy to kind of see that the lowest that the y value is ever going to be is just going to be 0, right? Because we're going to hit it. But what is the highest y bound, right? What is the highest y bound? Well, no matter where we are, we want to stop at this. We want to stop at this red line, right? We need to stop by that red line. Well, what is that red line? Well, that's the y value that's given by this equation right here. And you might remember this should look kind of similar from Calculus 2, that we could say, oh, well, that's just going to go until we hit the line y equals x plus 1. Now, a common question people ask is, how come you don't just put y here? Well, it's kind of weird mathematically to say y is less than or equal to y because these y values are not the same, right? This y value for the rectangular prism here and that y value for the rectangular prism here are not the same. These are not the same as the y value, the upper bound y value of this line. So we kind of we separate these things, we write it in terms of x to basically kind of delineate that these y values represent all the possible y values that we could get, in this region, and then we stop as soon as we hit the line y equals x plus 1. Okay, and so this right here, this is a description of this region, because look, maybe I should do some highlighting here. This region here, the 0 less than or equal to y less than or equal to x plus 1, that's describing all of this. Okay, that is describing everything here, right? This is all the space that is in between the lines y equals x plus 1 and y equals 0. And you'll notice that the overlap between those two areas, the overlap is exactly what we are looking for. It stops our little rectangular prism perfectly inside this region right here. Okay, and so when we're setting up our double integral here, we know, okay, double integral, there it goes. All right, and so this is our setup. And so we know it's going to be our function, which was 2x squared plus y. And then we know that one of our bounds is going to be from 0 to 2. One of them is going to be from 0 to x plus 1. And so the next question is, which bounds go where? Okay, which bounds go where? There's really only two options. Either we're going to set it up like this, 0 to, actually, here, I'll use the right colors, 0 to x plus 1, and then 0 to 2, in which case we set up our integral as dy and then dx, because remember that the first integral gets our first little dy there, and the second integral, the one on the outside, gets the dx. Or it's going to be this. It's going to be 0x plus 1 on the outside, and then 0 to 2 on the inside with our 2x squared plus y, and then dx and dy. Okay, so the question is, which ones go where, right? Which one is the correct variation? Well, let's take a look at this second one, right? Let's take a look at this one. So it's important to remember that, visually, we are supposed to be getting what? We are supposed to be getting, right, when we do a double integral, what do we get? Well, we should be getting volume, right? That's what we should get, okay? But if you solve this second integral, right? If we solve this thing, so we work from the inside out, right? Let's just pretend that this thing evaluates to something. I don't really care what it evaluates to. Maybe it evaluates to the number 3. Who cares? But the point is that when I do the next integral, the integral from 0 to x plus 1 of 3 dy, are we going to get a number? Well, no, right? We're not going to get a number. We're going to end up with something that has, right, if we were to do this integral that I just made up, we'd get 3y evaluated from 0 to x plus 1. We'd plug this in for our y values, right? We're going to get something that has a variable in it. This is not a number. This doesn't make any sense, right? Our solution, we're supposed to get a number for our answer. And so this is kind of one of the key things that's very important when we first learn double integrals. And the key idea is that this last integral here, this last one cannot have variables. Okay, it cannot have variables. No bueno, cannot do it. Okay, otherwise we don't get a number in our solution. So the only way that this is actually going to work, for us, let's make some space, is if we use the first option, right? And that is to integrate with respect to y first and then with respect to x. And since we're learning, let's just go ahead and do it. So we'll leave the outside one alone for now, 0 to 2, and let's go ahead and solve the inside one. Okay, and so we'll solve the inside one, and we'll have a dx on the outside when we're done. Okay, so how do we integrate the inside, right? How do we integrate 2x squared plus y dy? Well, remember that we get to treat x like a constant. So the 2x squared, when we integrate it, just becomes 2x squared y. And then how do we integrate y? Well, because we're integrating with respect to y, that's going to be y squared over 2. Right? And then we evaluate this from 0 to x plus 1. Okay, we evaluate from 0 to x plus 1. And so, being the clever mathematicians that we are, right, this is going to be the integral from 0 to 2. And now we just need to put this stuff on the inside of these parentheses. So let's see here. When I plug in x plus 1, I'm going to get, let's see, we'll stick with pink. So 2x squared times x plus 1, and then plus, let's see, what are we going to get? X plus 1 squared over 2. Now, technically, we're also supposed to put in the 0, but you'll see when we plug in 0 for the y's, we're just going to get 0, so there's nothing else to plug in, right? So we're going to get x plus 1 squared over 2, and then we still have our dx afterwards. And, this looks terrible, but this isn't so bad. This is actually, to finish, I'm just going to write, this is easy. Right? To finish this, you just multiply things out, right? Distribute. And you just solve, right? You solve it. You're going to get a number, right? This is going to equal some number when the dust has settled. And you're like, Dylan, why aren't you going and doing this? Because number one, I trust in all of your abilities to calculate integrals. If you couldn't calculate a basic integral like this, you wouldn't be here. And the second thing is because for me, the setup and really the first step here is the most important, getting here, right? After that, you can plug into a calculator and it'll do it for you. So again, I would still do the work by hand, but I'm going to leave this here for you to do on your own. Okay, now this is one example. So I would suggest that you pause the video here and maybe go back if you don't understand it, because I'm going to erase some of this and I'm going to go back to kind of do this problem again, but in another variation. Okay, so let's go ahead and tackle this same problem, but instead of doing it how we just did, right? I remember I said earlier that I picked to do the x bounds first. Okay, I said I wanted my x bounds to go between 0 and 2 because I knew it was going to be very easy for us to do. But what if I wanted to not do the x bounds first? What if I wanted to simply do the y bounds first? Okay, what if I wanted to say, let's try the y bounds first, right? Is there another way to do this problem? And the answer, of course, is going to be yes. Okay. So, all right, well, if I wanted you to pick y, I want you to pick y to go from between two numbers, right? What two numbers would you pick? Well, I would say I would like y to go from 0, right? Because here's our little rectangular prism, right? That's the base of it anyways. And it's going to hopefully go up and down between y and some value. And so the next question is, what is the highest y value that we would go to? Well, I claim that we're going to need to figure out what this y value is here. And thankfully, if you plug in x equals 2, hopefully we can see that this is going to be the point 2, 3. So not too bad. I'm going to just say, well, let's let y go from 0 to 3. And you might say, very astutely, Dylan, that gives us way too much, right? It gives us way too much. If I go from 0 to 3, right, and I say, oh, I can be any y value in this range, and I would be like, you're absolutely correct, right? If I let y go from 0 to 3, right, I'll shade this in for us, I basically am saying that I'm going to integrate over every single possible value in this range, which of course we don't want. So we clearly have to stop, right? We have to figure out how to trap it also in the x direction. Okay, we have to figure out, how do I stop it going this way? How do I stop it going this way? So let's try x next. So try x next. Okay. Now the upper bound for x, not too bad. It's just 2, right? That keeps us from going too far. Now, how far to the left do we go? Well, it kind of depends where you draw this box, right? It kind of depends on where you draw the box. If I draw this box down here, my left bound is going to be just x equals 0, right? But if I draw the box higher, if I draw the box up here, I draw the box here, and I say how far to the left, well, I need to stop. I need to stop by this red line. Okay, and so, you know, this lower bound is not so straightforward. Okay, it's not so straightforward. But hopefully we remember that back from Calculus 2, we actually tackled problems like this all the time. And so here's what I'm going to do. I'm actually just going to write out the solution, and then I'm going to talk about it, okay? So we need to still bound y from 0 to 3, but I claim that instead of going all the way from 0 to 3, we're going to break this down into smaller sections. I'm going to do two separate little trappings here. I'm going to trap y from 0 to 1, and then I'm going to trap y from 1 to 3. And you might be wondering, why am I doing that? Well, because if I draw my box down here in this value from y equals 0 to y equals 1, my left bound for the x value is going to just be x equals 0, right? And my right bound here is going to be x equals 3. That's fine. But if I draw the box higher, right? If I draw the box higher, like I said before, my left bound is actually this line. And so my x, the upper bound is still going to be 3, because if I draw the box to the right, I'm still hitting the line x equals 3. But what is my lower bound? Well, my lower bound is going to be, it's going to be the line, right? It is the line, okay? But we aren't going to write it as x plus 1, because that, when this doesn't make any sense, right? What we're going to do is, well, we already have the y variable, so it's a good idea to write this in terms of y as well. And so we just very quickly take this equation and rewrite it as y minus 1 equals x, and we say, oh, that's going to be our lower bound, because since you're giving me all these y values, that will inherently allow me to calculate all of the x values that are our lower bound. So I'm simply going to put that our lower bound here is the line y minus 1. And so what does this mean for us? This means that for the function 2x squared plus y, I believe that was the one we were working with, that in order to do it using, if we decided to describe y first, I would have to set up two sets of double integrals. I would have to do one, here's 2x squared plus y, and I'd have to set up another one for 2x squared plus y, where one of them has the y bound going from 1 to 3, right? So the y bound goes from 1 to 3, and the other one has the y bound going from 0 to 1. And then the x bounds go from 0 to 3 for this first one, and the x bounds go from y minus 1 until 3 right here. And then what do we do? So let's see, dx is first here, dx is also first here, and then dy is second, and dy is second over here. And this, I claim, is going to give you the same answer. This is the same answer. This is the same answer as the one we did before, which, just to remind you all, when we decided that we wanted to trap x between 0 and 2, the y value we said was going from 0 to x plus 1, and then it was just, our function 2x squared plus y dy dx. And in this other one, we decided we wanted to, trap y first, right? This was, we trapped y first, right? We said we want y to go between some numbers. And I claim that these things are going to give us the exact same answer. Now, you might also notice over here, by the way, that we could use Fubini's theorem if we wanted, because our bounds here are simply just rectangular in nature. So I could swap the order here if I wanted. I could actually do dy then dx. if that would make you happy as a clam. I just wrote it this way to kind of drive in the point that these outer bounds need to be numbers every time that we solve this set of double integrals. Okay, and that's pretty much it. This is the general idea. Now, clearly, I've only done one example. Do they get more complicated? Absolutely, right? There are several different variations of what this region could look like, right? We could have regions that are trapped between parabolas. Another question that you might get might look something like this. So, for example, maybe I decide to give you a double integral from -1 to 1, and I want to go from, let's see here. Let's make one up on the spot. Let's just do 0 to x squared of some function, right? F of x, y, and then I say this is dy dx. And a question you might get is to, swap the order of integration to get the same answer. Okay, and this is not as easy as you just swap them. You cannot just swap them and be like, all right, we call it a day, because we have to really identify what is this region of integration. We have to take a close look at this. And so maybe I might try drawing a small sketch of it. And I say, okay, well, I know what y equals x squared looks like, right? This is y equals x squared. That looks like a parabola, right? It looks something like this. Y equals x squared. And then from -1 to 1, okay. Oh, and I also know the line, y equals 0. That's just this here at the bottom. Right, so that's this. There's y equals 0. And then from -1 to 1, right, so here's -1, x equals -1. Here's x equals 1. So we're basically integrating over this region right here. And so, the question you might get is, how do you swap the bounds, right? How do you kind of go about doing this the other way? Okay, well, so the idea is that, in this example, we trapped x first. We trapped x first, and we did it. X has clearly got the easiest job, right? We just trapped it from -1 to 1. But now we want to trap y first. So now we want to trap y first. Okay, and so you have to look at this shape. We're going to have to solve for some points of intersection here, which hopefully, this is going to just be the point 1, 1, and this is just going to be the point -1, 1. And so clearly we can see that if we want to swap the order of integration, right, trapping y first now, what is y going to go between? Well, there's not much to it. Y is going to go from 0 to 1, right? That is going to give me all of this. Okay, that gives me a lot, right? And I don't want all of it. I need to next figure out, how am I going to stop the x from moving around too much? Okay, and so it kind of depends on where you are, right? It kind of depends on where you are. So let me do some erasing here to kind of clear things up. So the x is clearly, going to be trapped, let's see. Well, kind of depends on where we are. If we're on this right side over here, right? If we're on this right side, we can use the fact that x, it looks like, goes from what to what? Well, the upper bound looks like 1. And then what is the lower bound, right? Well, this comes from the fact that y equals x squared, but we can't just put x squared. We can't just y. We have to solve this and get that x is equal to plus or minus the square root of y. So the question is, which one do I use? And the answer is, well, for the right side here, it's going to be the positive square root of y, right? So this is going to be the square root of y. Now, that only gives us this region here. That only gives us this one. So we are also going to have to do it, and we're also going to have to do it for the other side, right? And so what is x trapped on the other side? Well, the lower bound, clearly, right, if I erase this to draw, I erased too much. Let's try that again. If I erase just a little bit here, and I draw my little rectangular prism, and I'm like, all right, it's going to slide to the right, it's going to slide to the left. The left bound is going to be -1. Well, what's my upper bound? What's my right bound? Well, it's going to be the negative square root of y. Okay, and this looks terrible, but it's not too bad. We weren't asked to solve it. We were simply just asked to swap the bounds. So if we were to try to execute this problem, and instead of starting with this original problem, you decided that you wanted to swap the bounds to make it easier on yourself, you would have to do two sets of double integrals yet again. We would have to do an integral from y goes from 0 to 1, and x goes from 1 to the square root of y of our function f, and then dx dy. That right there takes care of the right half of this region of integration. And then we would also have to add on the other region of integration. So y again going from 0 to 1, and x going from -1 to negative square root of y of whatever our function is, dx dy. And now we have, hopefully you can see, we have swapped the order of integration from dy dx. We swapped the bounds to being dx dy. And, sometimes this is super useful. It helps us calculate things quite a bit easier. Sometimes it's just an exercise for your little brains. Okay, so this is just a couple rough examples. This kind of talks about how to integrate over general regions, how we go about trapping things. I strongly recommend that you post any questions that you have or watch other videos, look at practice problems, things like that. Look at practice problems in the textbook and make sure that what they're doing lines up with what you've just seen in this lecture. And then, we're going to talk about in the next video, we're going to cover what happens when these bounds are circular in nature, right? What happens if they are round, right? If they're not just trapped between functions of x and y, what if they our regions of integration are round? And hopefully this should remind you of polar coordinates, because that is where we are going next. And we will do that in the next video.